Hi guys, these are magnetism problems for AP Physics. So the equations are on Moodle. I'll go through what they are as we do need them in the problems as well. So we'll just start with number one. Number one, a solenoid has 350 turns of wire and length of 29 centimeters. If the current in the wire is 5.4 amps, what is the magnetic field generated? So remember, a solenoid is a series of loops of wires that when you run a current through it will generate a magnetic field. So our equation for this is B, which is magnetic field, equals mu naught times I n over the length. So mu naught, remember, is a constant, and that is the permissivity of free space, so 4 pi times 10 to the negative 7th. Multiply that by the current, which is 5.4 amps, times number of turns in the wire, which is 530. All that over the length, which is 29 centimeters. Remember, that has to be converted to meters, so it should be at 0.29. We multiply all that out, we get our magnetic field equal to 0.0124 Teslas. This problem is using a coil of wire that's spinning in a magnetic field, and that coil of wire is going to have a voltage across it. We're going to figure out the maximum voltage of that spinning coil of wire. So problem 2 says a coil of wire with radius 50 centimeters and 300 loops is spinning with an angular velocity of 81 radians per second. The coil is rotating in a magnetic field of 0.0073 Teslas. What is the maximum voltage generated by the wire? So in this case, what we're going to use is V equals omega, so angular velocity, n dA, where n is the number of loops in the wire, b is the magnetic field it's spinning in, and a is the area of those loops of wire. This equation also has a sine omega t. That we are not going to use in this part. Cross that off. This is to find the voltage at a given time in the wire. We're just looking for the max. So when you're looking for the max, you do not use that part of it. So again, we'll just substitute in here. We have our angular velocity is 81 radians per second. Number of loops is 300. Magnetic field is 0.0073 Teslas. And last, we need to find the area of that wire, so that's going to be pi r squared. We have the radius is 50 centimeters, but again, we need to convert that to meters. So it's going to be pi times 0.5 quantity squared. And that's going to be the maximum voltage generated by this, and we should get 139.3 volts. For problem number 3, we're determining the voltage generated by changing the flux through a coil of wire. And we're doing that, we're changing the flux by pulling the wire from a magnetic field. That means the flux through the wire is going to be some number, and then finally it ends up at 0. So number 3 says if a 5.42 centimeter coil of wire with 145 loops is pulled from a magnetic field of 0.54 Teslas, if it takes 0.129 seconds for the coil to be removed from the magnetic field, what is the voltage created in the loop? So our equation for the voltage in this case is going to be V equals N times the change in flux, which is phi, over the time it took to change it. In this case, we've got N is 145 for number of loops. Now the change in flux is going to be the final flux minus the initial, and because it's leaving the magnetic field, it ends up with 0 minus the initial magnetic field, which was 0.54, times the area, which is going to be the area of the 5.42 square centimeter square coil. And so that we have to convert that to meters, so we get 0.0542 quantity squared, all over the time, which is 0.129 seconds. And we do that math, we get our voltage to equal 1.78 volts. Problem number 4 involves using a transformer to step up the voltage in a wire or in a circuit. Remember, a transformer involves two coils of wire next to each other, and the alternating current in one generates a alternating current in the other. So our equation for figuring out the current or voltage to a transformer is voltage to the secondary coil over voltage to the primary coil equals number of turns in the secondary over number of turns in the primary. So what we're looking for here is we're looking for the voltage across the secondary, and EMF stands for electromotive force, which is another name for voltage. Just remember that if you don't know what it is, it's probably voltage still. The voltage in the primary is 120. The number of turns on the secondary is 5815 over number of turns in the primary, which is 38. So we cross multiply and divide, so 120 times 5815 divided by 38, and we should get the voltage across the secondary coil is equal to 18,363 volts. Alright, so for this problem, we're going to be figuring out the energy saved by stepping up the voltage. So when the power company generates electricity, they will step up the voltage of that electricity because it's more efficient to send it through the power lines at high voltage, and then they step it back down when it gets to your house. So we're going to figure out how much energy is being saved in this specific example. Number 5 says a transformer is used to step up the voltage to send through power lines. The primary coil has 17 turns and the secondary has 3100. The generator producing the electricity produces 65 amps at 160 volts, and the resistance of the power lines is 1.4 ohms. How much power is lost when the voltage is not stepped up, and how much power is lost when it is? So the first thing we're going to need to do is use our transformer equation to figure out the new voltage when the power is stepped up. Voltage in the secondary, voltage in the primary, equals number of turns in the secondary over number of turns in the primary. So in this case, the voltage in the secondary is what we're looking for. Voltage in the primary is 160. The number of turns in the secondary is 3100 over number of turns in the primary, which is 17. We solve that, we get the voltage in the secondary is equal to 29,146. So that's our voltage in the secondary. So now we need to figure out the power of the source that's generating the generator. So remember, from the electricity unit, we have P equals IV. So this is for P equals IV will give us the power generated. So it's going to be 65 amps times 160 volts, and that equals 10,400 watts is being generated by this power station. Now, if we want to figure out the power lost, we have to use the P equals I squared R to figure out the loss in power. So for without stepping it up, it's going to be P equals I squared times R. So 65, 190 squared times the resistance of 1.4 equals 5915. So over half of the power generated is being lost if you do not step up the voltage. With the step up, we cannot use just the secondary voltage. We have to use P equals IV with the power generated to find the voltage, because the current is going to be lessened at that high voltage because the power has to stay the same. So since the power stays the same, we say P equals IV. So our power is the same from that previous one we found, so 10,400 equals I times our voltage, which was 29,146. Therefore, I equals 0.36 amps. Now we use the P equals I squared R to find the power lost. So we've got 0.36 amps times squared times our resistance of 1.4, and we get 0.178 watts. So a much smaller portion of the energy is lost when the when the voltage is stepped up. And reminder, in this equation right here, this is to find the new current when the voltage is stepped up, because the current does not remain the same when you change the voltage in this case. Number 6 is another transformer problem. In this one, however, there is one equation that is not in the PowerPoint on Moodle, so I'm going to include it here, and that is the root mean squared voltage is equal to 0.707 of the max voltage. And when we talk about root mean square voltage, because it's alternating current and because the current goes up and down, we have to figure out the average current or average voltage that is being delivered, and that is the root mean square voltage. So in this case, all we're going to do is use the transformer equation to find the new voltage and then convert it to the maximum voltage. So number 6 says a step-down transformer has 1,600 turns in the primary and 490 turns in the secondary. If the root mean squared electromotive force, that means root mean squared voltage, across the secondary coil is 120 volts, what is the maximum electromotive force or voltage across the primary coil? So we start with voltage in the secondary or voltage in the primary equals number of turns in the secondary over number of turns in the primary. And our voltage on the secondary is 120 over voltage on the primary, which is what we're looking for here, equals number of turns in the secondary, which is 490, over number of turns in the primary, which is 6,100. So when we do that, we get the voltage on the primary, and this is root mean squared, since it gave us the root mean squared voltage there. So it's going to be RMS. That's equal to 1494 volts. So now we say VRMS equals 0.707 times Vmax. We're looking for Vmax here. We end up with 1494 equals 0.707 times Vmax. And Vmax then is equal to 2113 volts. So let me know how this went for everybody. If you have any questions or concerns, please put them into the message boards on Moodle. Also, if there's any problems with like the quality or I went too fast or too slow, let me know in the message boards on Moodle as well. All right, thanks guys.